So today, another extremely important application of the integral, distance and displacement. So if we know the velocity of something, we can find the displacement. So in particular, the displacement is, this is really where we started with this, right? It was with a hummingbird, and I had a weird velocity curve. How far does the hummingbird travel? In that case, the velocity was all positive. So we could have velocity that goes positive and negative. So if the velocity goes positive and negative, then just the integral from A to B of the velocity gives the displacement, how far something is from where it started, and that's different from total distance, which is the integral from A to B of the absolute value of velocity. So displacement, we can say, is the integral of velocity, and total distance is the integral of speed. So, but you can't really practically do an integral of an absolute value in order to do the integral of the absolute value of velocity. What you really have to do to find total distance is separate the velocity integral into its positive and negative parts. So just a little discussion about that. So first of all, what is the difference between distance and displacement? If I start here and I go over here and I come back to here, all right, then my displacement is how far I ended up from where I started. That's called displacement. And my total distance is how far it took me to get there, total distance. So usually I think of displacement is what I want if I want to know where something is. So I have my rover on Mars, and I just want to contact it, send a signal to it. So I need to know its exact position. So I need to know its displacement from its original position. But if I want to know how much energy the probe has consumed, how much fuel it needs to make its journey, then I need to know the total distance because it went out, sampled some rocks and then came back over here and sampled some rocks over here. All right, so that takes more energy to do that than if it just went here and stopped, okay? We don't know why it did that, but I'm sure there was some important reason. All right, one of my favorite examples is the trip to the moon, right? So astronauts went out to the moon, they came back. What is it, 250,000 miles? Make that up. It's probably in the ballpark. All right. So when astronauts went to the moon and back, they started at Cape Canaveral, they launched, they went up to the moon, they landed in the Pacific Ocean, they picked them up, they took them back to Cape Canaveral. All right. Their displacement is 0. They ended up exactly where they started. So did they even do anything at all? Yeah, they went to the moon and back, okay? Their total distance is 500,000 miles, roughly speaking. I think those numbers are approximately right. All right, so there you go. That's the difference between displacement and total distance and how you calculate them. Can you say something else about that? No, let's just do some problems about it. Yeah, we'll just go into some problems. So the first thing I'm going to have you guys do is I have a worksheet called distance and displacement. So these are some problems that I made up about distance and displacement. So I'm going to do number 2 on this one because there's a weird antiderivative that we keep getting things like this, and we're sort of dancing around a topic that is to come, but it's a good dance, so I enjoy doing it. So number 2, we have a piston moving inside a cylinder. Interestingly, pistons moving in cylinders are about to become historical artifacts. So like talking about a steam engine or something. I'm going to say that within 10 years, nothing is going to have pistons. You're only going to find pistons in museums because cars are going to be electric. Anyway, these days we still have pistons moving in cylinders. Maybe some kind of like a pump or something might have a piston inside a cylinder. And it has a velocity with a sine curve, and that makes sense because I have a piston, right? So usually, the way a piston works, this is a piston for people who don't know. Maybe some people don't know this. A piston usually has some kind of a joint here so that it can attach to an arm, and there's usually a wheel. And then that wheel is going around and around, so the piston goes back and forth. All right, that's a piston. This is usually called something like a cam or a camshaft. So in a car, that's a camshaft. Piston goes back and forth. All right, so everything about the piston's position is going to have to do with the sine or cosine graph. All right, it's going back and forth. That's what sine does. All right, so our velocity, v of t, is 13.2 sine of 2t meters per second. Our time interval is 0 to 2 pi, and we're asked to do 2 things for each of these things. For each situation, sketch a graph of the velocity function without using technology, Then find the displacement and the total distance. That's two different things. This one's the integral of velocity. This one's the integral of speed. Okay. I'm not sure that was worth doing, but there it is. All right. So we're going to start with displacement. We're just going to start with a sketch of the velocity curve. So this is 13.2 sine of 2t. So please remember your pre-calculus. If I want to sketch that, then, and people use different symbols for this. This in here is always called a frequency. I always use the Greek letter omega, which is fairly common. Omega is equal to 2. So then there's something called wavelength, and wavelength is 2 pi over omega, right? So in this case, it's 2 pi over 2, which is 2. Sometimes we call this like L or P or something. It's wavelength. All right, so I use Greek lambda and Greek omega just because, you know, that's how they did in the college I went to. Some people use different variables for those things. All right, but so the important thing is that since the wavelength is 2, that means that the cycle is going to be completed. Oh, I'm sorry, 2 pi divided by 2 is pi, isn't it? It's pi, not 2. Okay, the wavelength is going to be completed at pi. So that means, you know, if I think about where what we usually call the critical points, although they're not all technically critical points the way we say it now, what do they call them, like crucial or important points? The significant points. There's like 5 significant points. There's 3 x-intercepts and a max and a min. And we also know that this 13.2 out here, that's the amplitude. That tells you how high and low you're going. So it's 13.2 up here, negative 13.2 down here. And this is a sine curve, so it goes meow, meow, meow. Remember I said the sine always goes through at a 45-degree angle? That's only if there's no coefficient up here, or just rather the coefficient is 1. Once there's a coefficient here, it's no longer a 45-degree angle. All right, so we've drawn a graph of the velocity curve. So our next step is to find the displacement. So the displacement is the easiest thing to do. It's the integral from 0 to pi of v of t dt. All right, so I'll let you go ahead and take a shot at that right now, and I'll finish it up in the next video.